Sure. Let me briefly introduce our speaker today. So today we have the pleasure to have Shangguan Chong from Shandong University. He will be telling us about some problems introduced by Brown, Erdős and Sós. So welcome everyone.
Okay, so hello everyone. So and I'm thanking Honglio for his invitation and introduction. So today I will talk about the sparse hypergraph problem of Brown, Erdős and Sós. So this is a classic two-round type problem, and it's very influential. So, in fact, it is a fantastic research area, and many interesting problems remain open. So this set of problems is deeply connected into other research fields of discrete mathematics, in particular theoretical computer science and coding theory. And I will survey some results and problems in this research area. So let's first to begin with some definitions. So I will use this bracket n to denote the set of first n positive integers. And this will serve as our vertex set of the hypergraph. So, and I will use this n choose R to denote the family of all R subsets of n. And an R uniform hypergraph, or R graph for short, is simply a family of R subsets of this bracket n. So H is an R graph and is a subset of n choose R. So here is an example about the final prime. So final prime is a 3 graph and it has 7 vertices and 7 edges. So you can see that it has 3 blue edges. It has 3 blue edges and 3 red edges and 1 purple edge. So it's a 3 graph. So what is sparse hypergraphs? Given integers VE and R, we say that an R graph is VE free if the union of any E distinct edges of H contains at least V plus 1 distinct vertices. Or in other words, for any distinct A1 to AE of the hypergraph, so the union of the AIs has at least V plus 1 vertices. So let's look at again the example of final prime. So you can see that the final prime is 4, 2, 3. It's 4, 2, 3. But this is because in the final prime, every 2, 3 edges have exactly 1 intersection. So the union of any 2 edges is exactly 5. So it is 4, 2, 3. And the final prime is also 5, 3, 3, because you can easily check that the union of any 3 distinct edges contains at least 6 vertices. But the final prime is not 6, 4, 3, because you can look at this set of 4 edges, 1, 2, 3, 3, 4, 5, 5, 7, 2, and 1, 7, 4. So this group of 4 edges does not contain the vertex 6. So it is a union of 4 edges. The union of those 4 edges contains exactly 6 vertices. So the final prime is not 6, 4, 3. Here are some more examples. For the base case, E equals 2. So we only consider the relation about 2 edges. An R graph H is V2 free if 4 distinct edges AB, the union of AB is at least V plus 1. Or in other words, the size of the intersection for AB is at most 2R minus V minus 1. So in other words, an R graph is V2 free if and only if it is an NR 2R minus V packing. So a family of R subsets of N forms an NR 2R minus V packing. So if and only if every 2R minus V subset of the underlying set N is contained in at most 1 member of the family. So we can, if R equals 2, so usually the graph case. So an R graph is V comma V choose 2 free if and only if it's KV free, if and only if it does not contain a complete graph on V vertices. So moreover, so an R graph is I free for all I belongs ranging from 2 to E, if and only if it has no cycle of length at most E, or in other words, it has girths at least E plus 1. So you can, from these examples, you can see that the notion of V-free graphs is a generalization of many well-studied extremal problems, two-round type problems. So from Erdős and Sós introduced the following extremal problem. So we use the function FRNVE to denote the maximum number of edges in an n-vertex VE-free R graph. So that is, given VE and R and N, you can construct a R graph with this number of edges that is VE-free. But for any R graph whose number of edges is strictly larger than F, you can find in this R graph E edges whose unit is at most V. So Erdős and Sós posed this question. So they want to study for fixed integers R, V, and E. So the asymptotic behavior of this function as n tends to infinity. So they also provided some basic lower and upper bounds for this function. For example, this is the classic lower and upper bound of BS. So you can see that in the upper bound, the exponent of n is the ceiling function of ER minus V over E minus 1. And in the lower bound of n, the exponent is without the ceiling function. In fact, this lower and upper bound is not hard to prove. So for example, so how to prove the upper bound, you can set K equals the exponent ER minus V over E minus 1, the ceiling function. Then you can check that for any, if a R graph is VE free, then for any K subset S can be contained in at most E minus 1 members of H. So S can be contained in at most E minus 1 edges. If otherwise, S is contained in more than, if S contained in some E edges of H, then the union of those E edges is small, is at the most V. So contradicting the assumption that such a graph is V free. So you can use a double counting the number of edges in H times the number of K subsets contained in every edge is at most E minus 1 times the number of all K subsets. So solving this inequality, you can show that this function has is of the order O to the power of is of the order n to the power of K. So this lower bound is also not hard to prove. You can prove it by standard probabilistic method. So you can set the probability P equals the order of n to the power of minus V minus 1 over E minus 1. Then you can construct an R graph by choosing every R subset of n independently with probability P. Then use the standard alteration method or the deletion method. You can show that with positive probability, such a randomly chosen hypergraph is VE free. So this how from Erdős and Sós proves the lower bound. But here comes the question: how tight is the upper and the lower bound? So you can see that there is an easy case where the numerator ER minus V is divided by the denominator E minus 1. In this case, so we can set the exponent to be some positive integer K. Then the corresponding value of F is of the order n to the power of K. So if you set this function equals K, then V equals ER minus E minus 1 times K. So basically the BES bound determine the value of this function up to constant factor, which is independent of n. So in this case, n is said to be the two-rank exponent of such V free R graphs. So where V equals this number. In the other case, where the denominator does not divide the numerator, then the upper and lower bounds of this function are far apart, are far from tight, because the exponent of n in the upper bound is an integer, but the exponent of n in the lower bound is not. So basically, you can study the asymptotic behavior of this function for any values of R, V, and E. But in this talk, we are mainly interested in the case where ER minus V equals -1 modulo E minus 1. So in this case, you can write the number of vertices V as in a following form. So V can be written as ER minus E minus 1 times K plus 1. So this formula is very similar to in the first case. So you only have a +1 here. So in this case, the Brown-Edge-Sós bound gives the upper bound big O of n to the power of K, and the lower bound is of the order n to the power of K minus 1 over E minus 1. So the upper and the lower bound in the exponent of n do not match. So in this case, people want to know whether there exists a real number of such that this function is of the order n to the power of alpha. So if such alpha exists, then we'll call it the two-rank exponent of this function. And if such alpha does not exist, then we'll say such V-free graphs do not have a two-rank exponent. So in fact, there are two conjectures, so which corresponds to the previous two cases respectively. So in the first conjecture, so people conjecture that for all fixed integers R, which is larger than K, and which is at least 2, and E at least 3. So this function, so the function in the second case, has order little o of n to the power of K, but is larger than K to the power of K minus, but is larger than n to the power of K minus little o of 1. So in other words, this conjecture asserts that for any fixed positive real epsilon, so the bounds over the value of this function divides over epsilon to the n to the power of K tends to 0 as n tends to infinity, and this function over n to the power of K minus epsilon tends to infinity, so as n tends to infinity. So this in particular says that there does not exist a real alpha, that this function is of the order n to the power of alpha. So I would like to mention that in the original paper of BS, they only posed this conjecture for a special case R equals 3 and K equals 2. So in the original paper, they conjecture that in a 3 graph, if the union of any E edges contains at least E plus 4 vertices, then the number of edges contained in this 3 graph must be of order little o of n squared. So this is the original conjecture. So to the best of my knowledge, so the current form of conjecture 1 first appears in a paper of Erdős and Sós. So this is conjecture 1. So for the first case, where ER minus V over E minus 1 is a positive integer, so people also have this second conjecture. So in this case, because we know that this function has order n to the power of K, so it is natural to know to ask whether such a limit does exist. So this conjecture is formulated by me and Tamo in a joint paper, but this is not the original conjecture of BES. So again, the original conjecture of BES only asks whether a limit exists for r equals 3 and k equals 2. So they ask if a 3-graph of any E edges contains at least E plus 3 vertices. So then this limit exists. So this is the two conjectures so concerning the function of FRNVE. Next, I will introduce the current status of the two conjectures. So in fact, the initial case of conjecture 1 is highly non-trivial. So what is the initial case? So the initial case is R equals 3, K equals 2, and E equals 3. So, and this case is solved by the famous paper of Erdős and Sós. So who shows that if a 3-graph has the property that the union of any 3 edges contains at least 7 vertices, then the number of edges in this graph is of the order little of n squared. And one can construct such a graph, such a 3-free graph with many edges. So the lower bound is n to the power 2 minus little of 1. So the upper bound is solved by the triangle removal lemma, which is one of the earliest applications of the vertices regularity lemma. And the lower bound is solved by a construction based on Beheren's 3-term arithmetic progression freezers. So after the paper of Erdős and Sós, so several other groups of researchers tried to extend the result to other parameters. In fact, people are able to prove conjecture 1 for several other set of parameters. So for example, Erdős, Franco, Rudel, Sarkozy, Circle, and Nagel, Rudel, Serhat, and many others have proved conjecture 1 holds for some other set of parameters. Based on their work, so up to now, we know that conjecture 1 is true for the following 2 sets of parameters. First of all, Alon and Shapira shows that conjecture 1 is true for E equals 3. So if you only consider the 3 edges, so the union of 3 edges, then conjecture 1 is true. And more importantly, this is the only case so that the upper and the lower bound of conjecture 1. So for other cases where E is at least 4, people can only prove either lower bound of the conjecture 1 or the upper bound of the conjecture 1, but not both of them. So here are the matching upper and lower bounds. So in a joint paper of Ganyan and me, so we show that the upper bounds hold for all integers R at least R is at least K plus 1 and K plus 1 is at least E. So in fact, this result is a standard application of the full power of the hypergraph removal lemma. So the first case that is not covered by this result is when R equals 3, K equals 2, and E equals 4. So this is the 7-4 problem. So which asks if the 3-graph is 7-4 free, then the number has order little O of n squared. So, and this is the upper bound. And about the lower bound, we can show that the lower bound of conjecture 1 holds for all integers R at least 3, K equals 2. And E belongs to 4, 5, 7, 8. And our method does not work for the case E equals 6. Because in this case, we cannot get rid of a 6 and 9 6 configuration, which is isomorphic to the 3x3 grid. So here is the 3x3 grid, which has 9 vertices and 6 lines. So this is a 9-6 configuration, but we cannot get rid of this configuration in our construction. So in fact, all the proof methods towards solving Conject 1 is in some sense inspired by the work of Erdős and Sós. So people always use regularity method to attack the upper bound. And for the lower bound, people always connect the construction for the lower bound to some solution free set. So maybe the solution free set is not the arithmetic progression free set in the work of Erdős and Sós. It has some more involved form, but it's always a generalization of the balance construction. So although for other cases people cannot prove Conject 1 in a full generality, people are trying to approach Conject 1. There are some asymptotic upper. So the Conject 1 says that this function, the Conject 1 says that the value of this function is has little o of order into the power of k. So if you place a +1 here, so Sarkozy and Shirko proves a weaker result. They show that the number of edges is little o of n to the power of k if you replace this +1 by this log2 of e. So this is a weaker result, and the proof applies the graph regularity method. In a recent paper of Koren, Gishborner, Lorentzov, and Shapila, so they managed to improve response by a log e factor. So, and their proof applies the hypergraph regularity method. So you can show that although we are coming close to the conjecture, but there is still a gap. So in other direction, Kivash and Long proves the upper proof that given any small constant epsilon, given any smaller than constant epsilon. So if the uniformity R is sufficiently large, if the uniformity R is larger than R0, which depends on epsilon and k, then they can prove this upper bound. They can prove the conjecture, basically, epsilon times n to the power of k. But note that in a conjecture, R is a fixed integer, but in the work of Kivash and Long, the uniformity R depends on epsilon. In fact, the dependency of R on epsilon is quite huge. So here, the R0 epsilon comes from the graph de Moivre lemma. So the result of Kivash and Long is still weaker than a conjecture because their R is not fixed. So what about the asymptotic lower bounds? So the original work of BS proves the lower bound is n to the power of k minus 1 over e minus 1. So in a joint paper with Zaki Tamo, we are able to improve the lower bound by a polylogarithmic function of n. So moreover, we can show that our R graph is not only has this V-free property, it's also IR minus I minus 1 comma k I free for all I ranging from 2 to e minus 1. In fact, this property shows to be important for some applications. So to prove this improved lower bounds, our strategy is that we relate the value of this function to the independence number of some approximate defined linear R graphs. So spirit, this logarithmic improvement of the lower bound is similar to the improvement of the independence number of locally sparse graphs. So in a parallel line of work, people use the improvements on the locally sparse. People use this strategy to improve the total number of surgically balanced graph. So this is a parallel line of work. So here is a very interesting question. So can we improve the lower bound substantially by some n to the power of epsilon? So maybe this problem is not that easy, but because in a parallel line of work, so people do not know people do not know an easy way to improve, to significantly improve the total number of of surgically balanced graphs. For example, the complete bipartite graphs. So now for most cases, people can only obtain this logarithmic improvement. So there are some variants of conjecture one, which is also interesting. So the original BES conjecture asks if a three graph has the property that the union of any E distinct edges has at least E plus 4 vertices, then the number of edges in this graph is little o n squared. So people found that to prove this BES original conjecture, it suffices to prove it for linear three graphs. So the linear three graphs has the property that the intersection of any two edges is at most one. So it's well known that to prove the BES original conjecture, it suffices to prove it for linear three graphs. So as in linear three graphs, any pair of vertices can be contained in at most one edge. So if a graph is three graphs is linear, then its edge can be viewed as follows. So we can be viewed as the following triple. So the first two vertices AB, we can put the third vertex in this edge as some function uniquely determined by AB. So and we can denote it by A circle B. So this function is uniquely determined by AB because it's a linear three graph. So Solimorsi has the following observation. So to prove the BES original conjecture, it suffices to prove it in quasi groups. So how can we come from a linear three graph to a quasi group? So quasi group, all of the axioms of groups except for the associativity. Given a linear three graph, we can add some identity E and set A circle A equals E. So we can just set the inverse of every element or to be itself. So we can have a quasi group. So because the quasi group version of the conjecture is equivalent to the original version, so we cannot. So it is we cannot hope to easily prove the quasi group version of this conjecture. But two groups of authors, Neradov, Sudakov, and Rom, they independently proved the BES conjecture in the groups. So if they prove that if G is a group and the order of G is sufficiently large, then consider the following family of H formed by triples of G. So AB and A times B. So this is the binary relation in G. So if they prove that if we consider a family of these triples, then if the family of these triples is E plus E, comma E free, so then the number of these triples must be little o of the order the G square. So basically, they prove the BS problem in groups. So the proof of Neradov and Suda cleverly uses two powerful theorems in combinatorics, namely the multi-dimensional similarity theorem and the density Hill-Stokes theorem. So the proof is very short but elegant. So there is also another variation of conjecture tools of conjecture one, which is very interesting. So is a Ramsey relaxation of this problem. The situation here is similar to the laws of the Van Waarden's theorem and Samaritis theorem. So we know that Samaritis theorem is a density version of the Van Waarden theorem. So here we can also consider a Ramsey relaxation of conjecture one. This problem is in fact posed by Cohen and Neradov. So they ask whether for every fixed integers r at least 3, k equals 2, and e at least 3, and a large enough n. So if H is if the R graph H is NR2 design, or in other words, H is linear, and every pair of its vertices is contained in exactly one edge. So this means the number of edges in H is exactly n over 2 over R is exactly n choose 2 over R choose 2. So the question of Cohen and Neradov is that if H has this property, then in every C coloring of the edges of H, one can find a monochromatic E plus 3, E configuration. So this means that, so in every C coloring of H, one can find E monochromatic edges whose union is at the most E plus 3. So there is some progress on this question. So Shapira and Timotkin shows that they can prove this Ramsey variation. So again, when R is sufficiently large. So when R is not fixed, but it depends on the number of current in C. But for C equals 2, but for C equals 2, the result is strong. They can prove that you can take R at least 4. But this left open the case for the case R equals 3. So two colors and when R equals 3. So again, this result of Shapira and Timotkin is slightly weaker than the question posed above. So because the R is not fixed. So these are two variations of the first conjecture. So now let's look at the current status of conjecture 2. So which says that the limit of this function always exists. So for the first case, when E equals 2, so we have mentioned previously that R graph is 2R minus K, 2 free, if only if the intersection of any two distinct edges is at the most K minus 1, or in other words, if and only if it's a NRK packing, then the result of Rado shows that this function frn 2R minus K, 2 is at least 1 minus little o of 1 times n choose K over R choose K. Note that this is already asymptotically tight, because in an NRK packing, as every K subset can be contained in only one edge. So the maximum cardinality of an NRK packing is at the most n choose K over R choose K. So basically, so the result of Rodel determines the limit of this function for E equals 2. So since the work of Rodel, so people found that the study of conjecture 2 is closely related to the study of the existence of NRK packings or NRK designs, or more generally, the study of conjecture 2 is closely related to the study of the approximate decompositions of hypergraphs. So people always use this tool to study this conjecture. So as Rudolph already solved this conjecture for E equals 2. So let's focus on the case E is at least 3. So the first case where R equals 3, K equals 2, and E equals 3. So the first case of conjecture 2 is solved by Glock. So he showed that if a 3 graph has a property, if a 3 graph is 5, 3, 3, then the maximum number of edges is roughly 1/5 times n squared. So as mentioned before, this result of Glock is based on the approximate decompositions of certain graphs. So Glock's result is based on the approximate decompositions of such graph HT. So here the HT has in the left you have V1 to AT T vertices. In the right part you have B1 to BT, again T vertices, and you have 2 vertices X, Y here. So HT is a graph of 2T plus 2 vertices and 5T plus 1 edges. So Glock put 2T 3 edges in this graph HT. So because you can see there are 2T triangles, AI, BI, A1, B1, X, and A1, B1, Y. So to AT, BTY, and AT, BTX, there are in total 2T triangles. So Glock put 1 3 edge in each of the triangles. So we have 2T 3 edges in total. And we can also do the calculation. So how do we get this lower bound 1/5? So consider a HT packing in a complete graph on n vertices. So the number of edges is roughly n squared over 2. So in a complete graph. So how many edges do HT have? So HT have 5T plus 1 edges. So roughly speaking, so one can put 1 minus little o of 1 h times n squared over 2 over 5T plus 1 copies of h in Kn. So there are this number of disjoint copies in Kn. And in one such copy of HT, Glock put 2T 3 edges here. So the total number of 3 edges given by this approximate decomposition of HT is roughly 1 minus little o of 1 n squared over 5. So this gives the correct bound, the lower bound of this function. So if if you can prove a matching upper bound, you can determine this limit exactly. So and you can show that such the 3 graph construct in this form is actually 5, 3, 3. So we managed to generalize Glock's result from R equals 2 to every uniformity R, which is at least 4. So the proof, and we can also determine the limit of this function. So the proof is based on a recursive construction with Glock's construction for R equals 3 being the base case. And this recursive construction is also comes from a decomposition of some approximately defined graphs or hypergraphs. So I think in the in the last few months, maybe in a month before, or so the current status of conjecture is significantly advanced by several groups of authors. So in the first paper in a work of this set of authors, so which including Jae-Hong Kim, which is a regular visitor of our IBS, they proved the conjecture 2 for all E equals 3 and E equals 4. And they can also determine the exact value of the limit. So their work is again based on some more strengthening of the hypergraph packings. So they call this method a conflict-free hypergraph matchings. Using this method, they can construct NRK packings which do not contain certain bad configurations. So this tool is developed by this set of authors. So basically, they can solve conjecture 2 for E equals 3 and E equals 4. And based on their work, recent work of Erdős and Sós, they basically proves the original conjecture of Sós. So they can the original conjecture of Sós states that if R equals 3, K equals 2, then the limit always exists. So the Erdős and Sós can prove the original conjecture of BES. So and based on that work, we can prove the BES conjecture for every uniformity R, which is at least 4. So yeah, so this but we cannot determine. We can only prove the existence of the limit, but we cannot determine it precisely. And this is the current status of conjecture 2. So so there are also some variations of conjecture 2 which may be interesting. So this is a generalization to the so-called Huygens-Steiner systems. So recall that an R graph is 2R minus K, 2, 3, if and only if it is a NRK packing, and the maximum size of such graphs or such NRK packings is N over K, is N choose K over R choose K. So if inequality holds, then such a R graph is called an NRK design. So the existence of designs, so for NRK satisfying certain necessary divisible condition, is a fundamental problem in combinatorics. So the initial case, so R equals 3, K equals 2, so was solved by Kalkman, so back in 1947. And the case R at least 4 and K equals 2 is solved by Wilson, so in 1972. So personally, I like this result because the result of Wilson shows that when you extend a result from R equals 2, from R equals 3 to R at least 4, such a extension may be not that easy. And so Kirash famously solved the problem of the existence of designs for every NRK, satisfying the necessary divisible condition. And but Erdős have this problem. Erdős conjecture that the designs not only exist, but also we can construct designs with some special properties. So in 73, Erdős conjectured that for all fixed E, and sufficiently large n, there exist N32 designs that are also 4-2-free, 5-3-free, and E+2, E3. So these three graphs not only form the design, but they are also sparse. So I just called such designs hypergraphs systems. So yeah, so several years before, Grok-Quinn, Rowe, and Ossos, and independently Bowman and Wagner approximately solves Erdős problem. They show the existence of N32 packings with this hypergraphs property, and the size of packings is 1 minus little o of 1 n squared over 6. So it is not exactly a design, but is very close. And in this work, Quan and this group of authors proves the Erdős conjecture. So in the full generality. And there are also two groups of authors, so which consider the generalization of Erdős problem from R equals 2, for R equals 3, K equals 2 to every R and K. So they can show that the existence of NRK packings with size close to the optimal value that are also 2R minus K, 2 free, or 3R minus 2K, 3 free, and ER minus E minus 1K, E free. So this is the result, but proof the exact equality here may be difficult. So as I mentioned in the beginning of the talk, sparse hypergraphs or V-free graphs has some unexpected applications in other areas of discrete mathematics. So in particular, theoretical computer science and coding theory. So in theoretical computer science, there are some applications of 6 free graphs in PCP analysis and linearity testing, and then they can also use it to construct some communication schemes, and then it also has applications in monotonicity testing. So, and in coding theory, so people use these sparse hypergraphs to construct some centralized code catching schemes, so which has applications in some networks. So and in particular, so in this work of Xing and Yuan, they used sparse hypergraphs to construct some optimal locally repairable codes, which has important applications in storage systems. So in their work, they found a connection, so between such codes and sparse hypergraphs, or more precisely, they used hypergraphs with no short batch cycles to construct these codes. And sparse hypergraphs also has some applications in list decoding. So in particular, the list decoding of Solomon codes. So as Hong has a paper on list decoding, I want to say a few more words about the connection between sparse hypergraphs and list decoding. So in list decoding, so we say so in list decoding, we say a code is not low comma L list decodable. So if there is a ball, so you can imagine a Hamming ball or a Euclidean ball. So if a ball, Hamming ball or Euclidean ball contains many code words, so or many vectors. So if it contains C1 to CL plus 1, if it contains L plus 1 vectors, then in this case, it is bad. This is a bad case for this decoding. We want to get rid of such case where many code words are contained in a small ball. So you can imagine that you can view these vectors as hyperedges of some hypergraph. So a small Hamming ball or a small ball contains many code words. In this is equivalent to say that those hyperedges are clustered together. So this means that the union, the size of the union of these edges is so here. This is the intersection. This is the connection of this problem to V-free graphs. And we can also use V-free graphs to construct some other problems like union-free hypergraphs and the consecutive hypergraphs. So this means this V-free graphs also has applications in extremal combinatorics. So yeah, I'm gonna talk and here. So you can see that there are many open problems. So yeah, and I think some the open problems here are interesting. So maybe you can work on it. So thank you. So I think my talk ends here.
Yeah. Any questions?